current seminar. So this week we have 2 talks, 3 presenters. The first talk is a paper review on deep learning analysis of blood flow sounds to detect arteriovenous fistula stenosis, which will be given by Nikhil, Kadivar, and Additi Pandey. Additi, first year PhD student in the Department of Applied Mathematics at Brown University. Prior to this, she earned her master's degree in pure mathematics at Imperial College London, UK, and her honors bachelor's degree in mathematics from University of Delhi, India. And Nikhil is a graduate student specializing in computational science at Brown School of Engineering. He earned his bachelor's degree in mechanical engineering from the India Institute of Technology, Madras. Before joining Brown University, Nikhil served as a research engineer at Robert Bosch, India. There he developed hybrid computational models that combine physics and machine learning. Without further delay, we will start the first talk. So, Additi, you can start.
Thank you for the introduction, Nazneen. Hello, everyone. So today we'll be presenting an interesting paper which was published in Nature Digital magazine recently, focusing on the use of deep learning to analyze blood flow sounds for the detection of arteriovenous fistula stenosis. I will present the motivation and the overall framework, and Nikhil will discuss on data analysis and the experiments. So we shall start off with hemodialysis and then proceed to describe what arteriovenous fistula and stenosis are. Hemodialysis is a life-sustaining treatment that uses a machine called dialyzer to clean the blood and essentially perform the function of kidneys for individuals with severe kidney failure. When the kidneys are no longer working efficiently, waste products and fluid build up in the blood. So dialysis takes over a portion of the function of the failing kidneys to remove the fluid and waste. Now for patients who are undergoing hemodialysis, vascular access is their lifeline, which allows blood to be removed, cleaned, and returned safely. Given its pivotal role, its global ranking as a top priority is apt, emphasizing on its significance in clinical research, patient care, and healthcare provisions. So what is AVF about? Before we go on to that, we'll talk about the vascular access in hemodialysis. So there are 3 ways that vascular access is created. First is through AV fistula, which is touted as a lifeline for vascular access in hemodialysis patients because it has numerous advantages to serve, such as lower infection rate and better blood flow. It is a surgically created connection between an artery and a vein before the start of the dialysis treatment. The second is AV graft. When AVF is not a viable option, we use AV graft, which is a synthetic tube connecting an artery and a vein. This third is catheter. So a catheter is usually a short-term solution. It is placed in a large vein, typically in the neck or the chest or groin, and is generally used when immediate access is required and other methods are not suitable. Out of all these 3, AVF is preferred for vascular access because it is very unlikely to get infected or cause any sort of blood clots. So as discussed before, an AV fistula, it is just a connection which is made by a vascular surgeon of an artery to a vein. And the surgeon places an AV fistula in the forearm or the upper arm. It causes extra pressure and extra blood flow into the vein, making it grow larger and stronger. The larger vein provides easy and reliable access to blood vessels. Without this kind of access, regular hemodialysis sessions would not be possible. Untreated veins cannot withstand repeated needle insertions because they would easily collapse. So that is the reason why we need an AVF. Having an AVF, however, does not guarantee that the access is going to be problem-free. There are cases of access infections and low blood flow, primarily due to clotting of the blood. Most common causes are due to stenosis, which is a significant driver of resource utilization, cost, morbidity, and mortality. So it becomes very crucial to be able to screen stenosis, and various methods exist, invasive and non-invasive both. Oscillation and ultrasound are convenient and non-invasive methods to detect abnormal blood flow, and they are indicative of potential stenosis. So changes in access, bruit or thrill during oscillation can be early indicator of a developing stenosis. It is measured using a digital stethoscope. So it is highly subjective and largely land on the listener's skill, necessitating the need for more objective and reliable methods. Therefore, the paper discusses about incorporating deep learning in analyzing the AVF blood flow sounds, which can be significantly cause an improvement in reliability and efficiency of stenosis screening by the healthcare providers. The paper talks about the blood flow sounds, which are recorded using a digital stethoscope at 6 different locations along each patient's AVF, where the dataset contained different constructions of AVF. The authors have pre-processed and recorded the one-dimensional blood flow audio signals into two-dimensional image representations to leverage the state-of-art models developed by the computer vision community. These models are trained using supervised learning with labels validated from a concurrent duplex ultrasound. So now let's talk about how the data was processed. The blood flow sounds recorded were one-dimensional time series, and they were converted into two-dimensional representations via a Fourier transform. Because the blood flow sounds cause leakage when using discrete Fourier transform, because they are non-periodic, hence we used short-time Fourier transform and MEL scale to obtain a MEL spectrogram. At the same time, the authors used another representation, which was a recurrence plot. Intuitively, just to recall, a Fourier transform tells us about the frequency content on the spectrum. So if anything is oscillating very quickly, we get bumps in the frequency content. However, if the oscillations are slow, we get lower frequencies. Leakage in Fourier transform is just when the data does not line up with the analysis frequency and it leaks into the surroundings. When the frequency of a signal is not exactly lining up with the frequency that is covered by the analysis, the signal will split over into the adjacent frequencies, and this can be prevented by windowing, which is to analyze signals in smaller manageable pieces so that the signal remains stationary within each window. In the paper, the audio signals are windowed using a hand window size of 512 and a hop length of 256. So there are like 512 samples, and we are basically multiplying this Hanning function point by point, and then taking the Fourier transform of the output. So hop length is 256, and it is usually given by whatever the length of the hand window is divided by 2. So divided by 2k, and in this case, k is 1. It just tells us that we can advance to the next window by 256 samples. And overlapping length is just to overlapping window is just there to ensure that there is no information lost at the edges. So we apply a discrete Fourier transform to this and then get our representations, which are then stacked to form a spectrogram. A MEL scale is a unit of pitch so that the equal distances in pitch sound equally distant to the listener. It just aligns with the human auditory perception, so it provides a more effective representation of the audio signals. The y-axis, which was the frequency axis, obtained in the spectrogram after the slide, was converted onto the MEL scale to form a MEL spectrogram. and the amplitude is converted into decibels. Then the other pre-processing method that was discussed was a recurrence plot. So a recurrence plot visualizes pair of time points where a system revisits similar states in its phase space. Here, however, it is applied into the frequency spectrum. So the audio signals from time domain were converted into the frequency domain through a Fourier transform, and then the frequency spectrum was divided into discrete points separated by an interval of delta, and the frequency spectrum is treated as a trajectory in the phase space, and each point, which is xtn, represents a spectrum state at some time tn. So if state xtm lies within an epsilon radius of xtn, then it is considered to be a recurrent state. And then an n cross n lattice of squares was generated, and the value, value of this was determined using a Heaviside step function. So if this is greater than 0, then it maps it to 1, otherwise to 0. This is just to ensure that there is consistent scaling from machine learning model input.
Right, so now I'll have a look at the data. So in the given study, the data set considered was of 433 patients, including both like post-ESRD, which is end-stage renal disease, and pre-ESRD. And there are a total of 2,565 AVS blood flow sounds were recorded, and each sound for like 15 seconds at a sampling rate of 4,000 Hertz using digital stethoscope. And the diversity in the data was also there. So there are 4 different AVF constructions were included in the blood flow sounds recordings, and at each AVF construction site, there were 6 locations were recorded to ensure that where the stenosis is developing along the AVF. And regarding the proportion of sounds, of the total sounds, 2,113 were patent, that means the normal, there was no stenosis. And at 452 recorded sounds were stenotic sound, there was shrinkage in the vessel. And the validation and testing in the study, a 10 full cross validation was applied to 10% of the total data set, and the remaining 20% was used as a held out for testing scenario. And all the results and comparison I'll do will be will have cross validation part included in it. So let's in the study, author says that cross validation was used throughout the experiments for model training, model hyperparameter tuning, and optimization, and comparing among different model architecture. So before moving to that, let's first analyze how the data looks like for the patent versus stenotic sound in the frequency spectrum. So as you can see here, the frequency spectrum is shown. The patent case is the blue ones, and the red ones are stenotic cases. That there is distinctly double peak here, which serves as the primary identifier, and each peaks represent different phases of the cardiac cycle. The lower frequency represents diastole, and the higher frequency signifies systole. Intuitively, Steno's AVS will elevate the jet flow Reynolds number, which will signal the possible onset of turbulent flow at the site of the lesion, where you have the shrinkage due to the stenosis. So now in the next thing, the author describes about average frequency spectrum in the training set. So here the idea is to gain some intuition about how the blood flow sounds differ by locations along the AVF, and how pattern and stenotic sounds differ from each other at each location along the AVF. So the author compared the average frequency spectrum in the training set, and as you can see from the figure, the area under the curve is higher for the stenotic case here, which is red, compared to the blue, which is the patent case. As this means that there is more loudness in the signal when you, which is also considered in the physical exam. So that's one thing, and this also gives some intuition that we should model each location separately when you are doing the when you want to predict the behavior, or when you want to classify them. So classify whether location along the area is stenotic or patent. So for this, the authors describe the experiment one, where you model for each location along the AVF. And for this study, they considered three different models, which was CNN, pre-trained, ImageNet pre-trained ResNet 50, and the vision transformer. And they studied these three models on two different pre-processing methods, which was MEL spectrogram and the recurrence plot. And the loss function which was used here for the model training was weighted binary cross entropy loss function. Now, this is usually to highlight the importance of minority class, as we discussed before in the data set. The stereotypic cases were less compared to the, which was only about 17% compared to the patent case. So to give more, to give more importance to the stenotic case, the authors used the weighted binary cross entropy loss function.
Nikhil, I have a question.
Yes.
What is the data imbalance? What is the minority versus the normal?
Wait, I'll go to this slide. So here we have out of total recordings, right? 265 blood flow sounds.
Okay. Yeah.
Only 83% of them were patent. And our idea is to find the stenotic sounds here, which is very less, right? So
Right.
I wanted to mitigate this.
Or 80 to 20, yeah, something like that, yeah.
About the two pre-processing methods, as you can see, for the MEL spectrogram, there were three different time resolutions were being considered, which was 368, 128, and 32 at the constant maximum frequency of 128. And for the reference plot, the two different resolutions were tested. There is motivation for this. I'll come to later why authors did this. And the metrics the authors reported in the paper to compare different model performance. As we can see here, one of the widely used metrics is measured the area under the curve for the receiver operating curve in case of diagnostic stakes. The idea here is the perfect classifier lies here on the top left corner. And the more closer the curve is to the top left corner, the better is your classifier. So as you can see in this figure, but sometimes this area under ROC curve could be misleading, because if you have a lot of true negative in your data set, then the denominator shoots up and it will lead to a higher sensitivity here. And you may be misclassifying your positive cases, but still your ROC curve will give you the good results. So for that scenario, authors also consider the area under the precision ripple curve. Here the idea is to see how the classifier is identifying the positive cases. It does not care about true negatives, which is the patent case here. So in this scenario, the motivation is the better the classifier, more closer to the left, to the right side of the curve. So both the metrics were used in the study, and I'll show you the results later. So the results for this experiment one, which is modeling for each location of area. The first result which author highlights here is spectrograms outperforms recurrence plot for all the three different network architectures considered. And the intuition here is because spectrograms contains information about time and the frequency, while recurrence plot can only have frequency domain. So the spectrograms outperforms recurrence plot in this regard. However, at first thought, it may be intuitive to believe that difference between pattern and stereotypic sounds are only encoded in the frequency domain, so why time should be important. But the next result will highlight why it is important, right? So the second result, what authors mention is the high resolution in time spectrogram outperforms the low resolution in time spectrogram, keeping the frequency part same. Hence, the time domain must be important. So also, this also further supports the argument that there are distinguishing features in the time domain and is consistent with the general idea that model performs better when you give more information to learn from. The next interesting results which authors mention is the vision transformer outperforms CNN and ResNet for the experiment one. And here the idea is the spectrogram has time and frequency on the x-axis and y-axis, right? Now, the CNNs are inherent to translation invariants. So for them, it's not logical to use CNN for this case, because you have invariance respect to the frequency axis, which is not good. Each different frequency has different importance here, so it will perform bad. Also, the other thing which is important here is the The relevant frequency for sound events are distributed non-locally, which also contradicts the locality bias in the CNNs. While in case of vision transformer, it uses the self-attention mechanism. So in that case, it can explore the parameter space more freely from every layer. And also it has a wider receptive field, which we call it global receptive field at every layer. So it is able to interpret spectrogram in much better sense compared to CNN. And the next experiment, which authors also mention, is how it is important to contextualize sound with the location. So as we mentioned, there are 6 locations along the AVF where the sounds were recorded. Is it a good idea to even give some information about the location? So for this experiment, authors develop a universal model where all the locations with their position encoding, like location metadata, was provided to the vision transformer for the spectrogram as a pre-processing method. So as you can see in the figure, to the flattened feature vector, the metadata was being provided, which is in the 3 scenarios they tried, which was integer encoding, one-hot encoding, and the learned embedding matrix. Ideally, it should not matter that what encoding you use here. We expect model to learn, but the paper disagrees, and it provides better. It shows that the learned embedding matrix gives better results for this case compared to the other 2. And as you can see here in the matrix, which is AU ROC and AU PRC, the higher the better the values. So in universal model with no location metadata, the results were a little bit less better than compared to the universal model with location metadata. As you can see, both the metrics were high. So that means the sound must be contextualized with location along the area. So overall summary, which we discussed from experiment 1, 2, and 3. So the overall idea is vision transformer trained on high resolution in time spectrogram for individual locations performs the best, as you can see from the sensitivity, specificity, and F1 score. So at all the locations, the individual location-based models are much better. Now the calibration plots. Here is one important thing which we need to understand is the predicted probability are much higher than the it's biased towards this side, right? So the idea here is, since we use the weighted cross entropy function, loss function, we try to mitigate the imbalance in the data, so the model becomes overconfident in predicting the stenotic case. So all the probabilities which we are trying to get from the model, it's higher than what it should have been from the empirical perspective, right? So this is one study which is kind of a limitation of a model. Now in the next experiment, the authors wanted to check, is it possible to distinguish where the blood flow sound is coming from? Like, let's say, if I distinguish whether the sound is coming from radial or in the brachial artery. So the answer is yes. In this case, it's possible because the structure is different. The brachial artery is almost 2 times larger than the radial artery and has thicker walls. So the sound characteristics are different, and the model is able to predict well, classify where the sound is coming from. And you can see from the mean ROC, it's 0.78, which is good value. For the next experiment, what they try here is, can I distinguish between cephalic versus basilar vein blood flow sounds? So in this case, no, it could not. As you can see, just a chance like at 0.5, you have a curve which is going closer to that. Because the difference between cephalic and basilic vein is only 1 to 2 diameter in general, so the sound characteristics are very similar. That's why the authors argue that it's very difficult for model to distinguish where the sound is coming from. And then one more experiment which authors mentions here is, is it good to contextualize the sound regarding the anatomical origin of AVF? As I mentioned before, there are 4 ways you can construct AVF, depending on what artery and veins you are using to construct it. And is it good if you modify the vision transformer and provide the categorical encoding of the anatomical origin of the AVF? So in this case, what authors present here, the model did not improve, the comparison was same, the results were almost similar. So the overall conclusion over there is that there's no information being encoded in the anatomical origin of the artery or vein, which the model could leverage. So the overall key points to take in the study, in summary, the study presented a novel, fast, and easy approach for screening of AVF stenosis in hemodialysis patients using deep learning to analyze the sound of AVF blood flow. The final model, which was recommended for deployment, were the individual location-based vision transformer models, which were trained on 368 and 120, which is high resolution spectrogram images. The preliminary model evaluation showed that the proposed technology can screen for stenosis at a level comparable to that of the nephrologist performing the physical exam, but with the advantage of course, being automated and scalable, which is very important. The clinical implication is that the proposed new screening tool can help cases of stenosis that may otherwise be missed due to the understaffed dialysis centers. As we can see here, the patients to staff ratios at some of the dialysis center can exceed 9:1, which is also like 3% higher than the recommended limit from the National Kidney Foundation. So in this case, this kind of method or approach will be very, very useful. Also, there is potential for this technology, which could be patient-facing. The next step could be implementation, like deploy the model onto a server and create an API so that users can upload the record and upload the sound and receive the prediction. Some limitations of this study. So in the study which was considered, only the brachial, radial, and cephalic basilic fistulas were studied. There are other ways also which are considered for constructing the AVF, but which were not addressed in these studies, where the model may not generalize. The one more thing is the framework could not identify stenosis on the arterial side of AVF because it's quite rare, and there are only 6 samples out of 441 stenotic samples were present in the study. So it's very hard for model to predict on this side. And another important clinical implications of adjusting for class imbalance during the training process is that it can potentially cause the model to be miscalibrated. In the given case, authors were using a weighted loss function in case like oversampling the minority class, which can potentially cause the model to be overconfident when making positive class. This stenotic sounds prediction. Another limitation of this study is how data was validated. Like in this case, the stenotic lesions were identified with duplex ultrasound, but clinically, a stenotic lesion identified on ultrasound does not always necessitate angioplasty, like procedure treating AVF. So this is maybe another limitation, but it's very good tool for identifying the stenosis, of course. So that's the end of the presentation. You have any questions, suggestions, or comments?
Thank you, Nikhil and Additi, for your great presentation. So is there any question for the speakers?
I have a question, Nikhil and Additi. Why do the authors say why the VIT, the vision transformer, gave better results, or just reported? Do they explain?
Sure. So in this case, CNN cell translate. So here you have frequency on the plot. Let's say if you have a natural image and you want to classify, if cat is in there in the left corner or the right corner, it does not matter for CNN. It's just a cat, right? But in this case, where you are trying to identify that pattern in the frequency domain matters. Like if it's on the at which location on the spectrogram plot, you have that particular pattern. It's very important here. So that's what the author is trying to highlight here, that why vision transformers does not have the inherent biases, which is locality bias, and also the translation invariance, which is present in CNN. The vision transformer does not have that. It has self attention mechanism by which it captures it. Did I answer your question properly?
Yeah, I was just wondering. I mean, yeah, it does make sense, but I was wondering if they have a quantitative study, like an ablation study, to see why that.
Only plots they provided here was this table, where if you follow through numbers, it makes sense. But other than no, I don't think they cover anything more than that on this side.
Also, I have a question on the imbalance data, because we have done this type of work before, and oversampling the minority class using weighting is actually creating a bias. So it's not necessarily, there are other methods to more modern data augmentation methods to deal with the balance. In the paper of Yeonjong on the hypoxia. So do they say anything about that, the bias in the oversampling the minority class?
Professor, I'm not aware of the paper you mentioned. I think so.
But in your conclusion, you had the bullet about the imbalance of data.
Yes, that's like I mentioned in the calibration plots here, right? So that's where authors are trying to explain why we are overconfident in predicting it, because we adjusted the loss function accordingly.
Yeah. But what I'm saying, that creates a bias, or when you go to new situation, you may need to recalibrate that, but you don't know, of course. So
Yeah.
it's a little tricky. Calibration is not universal.
Yes. That's interesting.
Yeah. I mean, that's the holy grail in these cases with the data, because the class that you're interested in is highly undersampled. Here was 2-1, right? Basically. 80%, 20%, less than 20%, 17%.
So is there any other questions? I think we are done with this presentation. And Professor Shin, are you here?
Yes, I'm here.
Thank you for joining earlier. Can you share your screen to see if there is any problem?
Yeah, sure. Can you see my slide?
Yeah. Thank you so much. So we move on to our next talk. Next talk is on the training and generalization of deep operator networks, which will be given by Professor Shin. Yeonjong Shin is an assistant professor of mathematics at North Carolina State University. He completed his PhD in mathematics from the Ohio State University. Before joining North Carolina State University, he was an assistant professor in the Department of Mathematical Science at Korea Advanced Institute of Science and Technology. And before that, he was a Prager assistant professor in the Division of Applied Mathematics at Brown University. In 2022, he received the Sangsan Prize for Young Mathematicians from the Korean Mathematical Society. So without further delay, we will start the next talk. You can start.
All right, thank you so much for a nice introduction, and glad to be back in Crunch seminar. So today I was going to present my recent work on DeepONets, and this is joint work with Sang-Yen Lee from FSU. So I know that everyone is familiar with DeepONets, but I just to bring some, slide for motivation. So now you may see many incidences like AI for science and scientific machine learning, along with like great challenges in science and engineering. And more recently brought my attention to the weather forecast and also Earth visualization. So here I'm showing you part of the video where the NVIDIA CEO, Jensen Huang, gave a keynote speech on EVE. And then we are talking about by utilizing NVIDIA's GPU, what great things can happen. And one of them is actually creating a virtual Earth. So this is the left is the actual Earth, and the right is their corresponding digital twins. And with that, they are claiming that they can accurately predict some of the weather features. And one of those things can be allowed by utilizing so-called operator learning framework. And operator learning framework allow us to do super fast simulation or inference almost instantaneously. And one of the representative models are out there, especially the weather forecast. And this is the one post I found recently. One of the claims is that the three of the machine learning weather forecast model are capable of predicting some behavior of the Hurricane Lee, so that what it says is the consistently forecasting landfall between Cape Cod and Nova Scotia. So this is the one model called the GraphCast, and this is a forecastnet and Pangu weather, etc. So this somehow justifies why people cares about so-called operator learning. And it got me to think that, all right, the super fast inference does not imply accurate inference. So that actually starting of this motivation of this work. So that it got me to think, then what are the core components in this operator learning process? So in my perspective, there is a first component should be neural operator in terms of like specific neural network-based model for approximating operators, and one of which is the DeepONet, of course, is a first place here around. So, but that is not the end of the story. We have also training protocols, like how we process the data, then how we optimize them over. And by combining these actually give us some inference accuracy. So more easy word is a generalization performance. But if we look this process more carefully, we know that almost all neural operators proposed these days are universal approximators. So in theory, each and every model should do a good job in approximating certain operator of interest. So this suggests that actually this itself does not imply some accurate inference or good generalization performance. Actually, one of the main reasons that why there are many neural operators out there is to improve the inference accuracy by means of something. And also, we know that training itself also does not imply that good generalization performance because there is some inductive bias. So the goal here, the motivation of this work is to understand the interplay between this optimization by means of the training protocol and its effect to the generalization within the DeepONet framework. So here is a set of the operator learning. So suppose G is our operator of interest. Here, X and Y are in ideally infinite dimensional function space. And we get a collection of some data so that Fk is a function belongs to X and Uk is the corresponding output through operator G. But we cannot really plug in function informations into the computer so that we often tend to discretize them in the following way. So input function F tends to discretize in XMX dimensional finite dimensional space. And UK is often solved by some traditional FEM solver on a certain grid point so that we have certain amount of the information corresponding to UK. And the learning task is to learn neural operator using those data. And that's the task. But what we really want is the trained neural operator that works well on the class of function in a reasonable way. So that is corresponding to the generalization. So let me give more detailed explanation of what do I mean by generalization. So currently many neural network model has been proposed and mainly to improve the more robust and generalization performance claimed. But many of them have actually the universal approximation property. Then why this kind of discrepancy might happen? Because both are satisfying the universal approximation property, but one also has one same property, but what makes the key differences? So in this talk, I will focusing on DeepONet from the Crunch group. So that is simply speaking, DeepONet is inspired by the universal approximation theorem, and it's in its own architecture can be viewed as in a product between the branch network, which is the yellow here, and the trunk network and in the product. And here, N, I'm not sure what N is called in the literature. I asked once Lulu what N is called, and he said, we didn't name for it. So I gave a name. He said width of the DeepONet. But if you happen to know what N is refers to, just let me know, then I can correct it. But at the moment, let's say this is the width of the DeepONet. And input f is the discretized function from a certain f, and output is a function of n, y. So overall training task, the overall parameters of the DeepONet is the collection of the branch parameter zeta and the trunk parameter mu. So that is the architecture. Then training task goes as follows. So we want to find the DeepONet parameters that is approximately fit the what's given in our data set. So here K represents the number of the data point, data as a pair, as a function. And here I represents our output function sensors. And typically MSE is formed, and training refers to minimizing this loss function. And popularly first order method are used, but it often fails to minimize the loss sufficiently. Accordingly, DeepONet doesn't produce a reliable inference result, resulting in poor generalization performance. And moreover, in many cases, and in almost all the cases, both networks are simultaneously trained. So here, let me illustrate one instance that DeepONet are struggling while using standard method, ADAM. So I will go into over the details this example later on, but here the operator of interest is the following. So given the pressure field, we want to recover the discontinuous conductivity as a function so that you give a smooth solution as an input, and we want to get the output as a discontinuous solution in the following form. So this is a training loss versus the number of iterations. And here red indicates the standard training way of DeepONet. So just apply ADAM and the loss function that I show you, apply ADAM, and this is how you get. So that is somehow stuck at the level of 10 to the minus 1 and seems no improvement after that. And this blue one is the proposed one I will going to introduce in more details, so that in terms of the training error, training loss, then actually we are 5 orders of the magnitude smaller when it is compared to the standard way. So that is the one motivation. So while you have high loss through existing optimization method, we cannot really tell that that is somehow well trained, or we cannot really judge whether our model is lack of capacity in terms of learning the target operator. So here is our strategy. So motivated by the divide and conquer paradigm, we divide 2 steps. So we divide the entire optimization steps into the 2. So one is we are going to focusing on training trunk network only. And the second step, as a result we get from the first one, we are going to learn branch network accordingly. So the motivation of developing this, proposing this two-step training method is as follows. So one is the matrix representation, so that we look carefully on how this loss function being constructed. Then we have 2 double summation, which is one is with respect to the number of the data in terms of pair, F and U pair, and Y, the I index corresponding to the output sensor point. So that when we actually make this as a vector notation, so that reduce the one summation with then this is what we get, so that we just vectorize each and every with respect to the output function sensors. Then this is just a vector summate, the vector subtraction with the standard Euclidean norm. And by recalling this in a product structure that DeepONet has, actually we can separate this into the like fundamental-like matrix, which only involves the trunk network information, and the coefficient can be thought of as a branch network information on K. So at this point, now we can actually further reduce this summation to matrix form, because when you add one more K, then you can think of just adding one more columns on the coefficient side and also output function side, so that this is what you are going to have at the end in a matrix form. So up to some normalization constant, like divided by the number of the data point, etc. Then if you look at this closely, then the first component matrix looks like the Vandermonde-like matrix, which is only formed by the trunk network. And the disk coefficient matrix is actually formed by the branch network, and U is our output data matrix. So with this observation, so our and also one more motivation observation being involved. And we're going to apply so-called reparameterization trig in DeepONet structure. So this is a standard DeepONet architecture, so that coefficient, basis, type, so that this is the vectorized notation, so that just collection of all the trunk network in terms of last one width, and the C is just a vector of collection of all the coefficient, the branch network. So this is a standard one, but the one we introduce is the following. So we introduce a square matrix, which is trainable, and we thought about this neural network in terms of the following. So that now T being multiplied in between, and then we view together with this T as a new trunk network. Let me a little bit go over explanation why we introduced the T, but at the end, now this as a new trunk network, then by multiplying the branch network, then this is the similar matrix representation with this reparameterization trig. Okay. Then with that, so our goal is now to train mu and T and zeta. So after we are figuring out what is the mu, T, zeta, then this is our neural network neural network DeepONet. So the first step is concerned with the following optimization, so that when you compared with the previous goal, actually we just T times C zeta, which is the branch network part, is being replaced by just a simple matrix A. So A being replaced by just a constant, the coefficient values, and then we are going to optimize over mu and A. So that is the first part. Then once this part is done, then we are going to get mu star and A star, which that minimize this quantity. Then we need to decide the T as well. So that the way we decide T is we are going to apply QR factorization on this Vandermonde-like matrix formed by the trunk network, and then set T star as a R star inverse, which is obtained from the QR factorization. But note that QR factorization can be thought of as a orthonormalization procedure, so that you can think of this actually can be viewed as we are going to apply QR factorization on the trunk network, so that each of the trunk n are orthonormalized with respect to the point we have. Then we decided mu star, T star, which completely determines the trunk network. So that's the step one. And the step two is concerned with the branch network, which is just the C part. And then our targeting so we want our trunk network, the branch network, to fit this R star times A star in Frobenius norm sense. But this problem is merely just a regression problem in the multi-vector valued neural network, so that it has been widely known that with a certain overparameterized case, we can achieve the zero loss under mild conditions. So that's the step two. And then zeta star is being determined, so that everything is determined. So that's our proposed method. And here's some remark on the use of the T. So actually the use of the T does not change expressivity of the DeepONet, because if you think about the feed-forward neural network being used for the trunk network, the last layer is just multiplied by another matrix T. Then that doesn't really change any of this expressivity on the top of this, what DeepONet already has. And as I mentioned, because we are going to apply the QR factorization, that is viewed as applying Gram-Schmidt's orthonormalization process on the trunk network. By applying the orthonormalization process, actually branch networks know what would be the best value to learn for them for the second step. Now, numerically, we've also found out the use of the T dramatically improved the stability and also generalization ability, so which I will going to get to later in a moment. And natural question in terms of the theoretical perspective is then, all right, so is this two-step procedure is equivalent to the original one in what sense? So we have actually proved that actually the minimum, so this, the right-hand side is the minimum you can achieve from the standard approach, just training trunk and branch simultaneously. And if there is a minimum, then actually this can achieve the same minimum. And furthermore, this somehow separation actually allows us to prove the zero training loss by DeepONets. So by just considering just simultaneously actually might be challenging, but this is one thing we proved, so that zero training loss can be possible, and that is rely on the following theorem utilizing the trunk network interpolating SVD idea. So we can actually explicitly construct a deep neural network for the trunk net, and then it satisfies a certain condition, but this basically tells you that trunk network is capable of learn the SVD part of the data matrix U. So one thing might be surprising, actually, what makes me a little bit surprising is there is a flaw in the architecture. It's quite specific architecture, which means that there is some dimension reduction you can achieve, which is the full in a certain sense, then actually you can do as good as what SVD can do. So that is actually plays a role in showing this zero loss analysis. Before I go to the generalization error analysis, let me show you how this new method performs on some numerical test first. So we considered three operators you can think of from these Darcy flow equations. So the first example is concerned with the fourth problem with the nonlinear conductivity. So that given these parameters, so our interest is given kappa, we want to predict the pressure field P. And in that regard, actually, we use this, we design our input function space as a constant function space. And the corresponding data were generated from, finite element solver. And in this case, we have 2049, the output sensor data point. And input data sensor point is just set to 1 because it's a constant function. And here is the loss comparison, so that the left, because we have two stages. The first stage is training the trunk network, and the second stage is training the branch network. And the first stage actually corresponding to the entire training loss by the vanilla training simultaneous monolithic training procedure. So that here I show the training loss, and the red shows but it's just the ADAM, applying ADAM, and the second, the two-step blue one is the proposed one. And this is the loss trajectory for training trunk network. And you see that order, at least 2 orders are smaller than what vanilla training can achieve. And on the right-hand side, I show the branch training loss. And you see that actually we compare with without QR factorization versus with QR factorization. So the blue shows the with QR factorization and green is without one. And you can definitely see that the benefit we can gain by applying the QR factorization, so that loss goes down to like 10 to the minus 6, 7, 8-ish part. So in both cases, we can think of two-step were successfully trained. All right, then this is the training part. Then how this is related to the generalization performance. So here I show you the relative L2 error on unseen 1,000 test cases. And the blue shows the relative L2 error by two-step training method. And the red is result of the standard monolithic training method. And the green is the two-step, but without QR factorization. So this clearly demonstrates you that importance of using QR factorization after training the trunk network, in a sense. And also you may see that the square and the circles, and let me a little bit explain what this means. So that is actually indicates the relative L2 error of conditional optimal sense. So what I mean by conditional optimal in the following sense. So suppose the trunk network is being fixed, then this is corresponding to this part. And hypothetically, we have given F test, we know what U test. Then actually we can solve for the least square to get what would be the best least square coefficient if U test being available. Then the least square solution, corresponding least square solution, should be the one that branch network can shall predict when we plug F test as an input. So this provides some conditional optimality in the sense that assuming that our trunk network being well trained, then it actually can be measured how well the branch network is generalizable to unseen data point, unseen function input. So this is our relative L2 error, and what it implies is that the following. So two things. So one is, if this error is small, then we can ensure that the trunk network is well trained in the sense that they are capable of representing what output function values, which is U. And another thing is I just mentioned is that it can actually see how branch network are well trained in the sense of the generalization perspective. Then with this perspective in mind, let's go back to the figure here. Then by trained by the deep two-step method, you can see that this blue is almost identical to the black circles, which tells you that the branch network trained by two-step is well trained in the sense that it matches the best least square solution. Also, when it is compared with just a vanilla, this square is slightly above than the circle one. And this tells you that the two-step is more effectively learn the trunk network in that sense. So this red and this circle and the square actually provide quite a useful indicator on which network architecture you may want to change. So in this case, we just simply run it and found it worked well. So, and also another good thing about this two-step is I found in practical case is that I can just separately train the trunk network, see if the weather loss is sufficiently small enough. And once it is all done, then I can just extract the corresponding branch information and just train the branch that separately until it gives us a satisfactory result. So it actually provides a practical convenience and also measure which architecture you may want to pay more attention to it. All right, so that was the first problem. And the second example is the following. So now we are concerned with the inverse problem, which I show you briefly earlier. So that now our operator of interest is as follows. So given the pressure field, we want to recover this continuous conductivity kappa, which is the piecewise constant in that way. So that we we generate the data, just solving at least finite element method, and this is our resolution of the data, and we generate the 1,000, spread 900, 10, 100, training and test, and this is the result. So here is again the loss figure that I showed you earlier, and this is the branch network training. For this branch network, we specifically utilize so-called active neural least square that I developed with the Mark Ainsworth, so that any method can be applicable. But in this case, actually, with just a two-layer neural network, actually, you can achieve the quite good accuracy in that regard. So partially to advertise this method, and partially it works great in this particular example, so we employ it, but any method can be applicable. And this is the relative L2 error. And you can see that the vanilla method actually learns trunk network fairly well. However, you see that big discrepancy occurs, and that is because of the simultaneous training was not very effectively learned the branch network in that regard. So that's why you see the big discrepancy. And on the other hand, actually, two-step method actually approximate both the trunk network and the branch quite well compared to what's out there, the simultaneous, the ADAM training. And you see that except for the very small values here, almost optimal branch generalization is achieved, and also way better performance in learning trunk network. So the separation actually allow us to interpretate what might be we may want to focus more, or what might we need to change more. So in that perspective, actually trunk network performed pretty well in learning the representation of the output functions, and the remaining goal is to capture all the details of the branch network. Yeah, and this is absolute error plot, so that this is the vanilla training and beta 2.02, and this is ours, so roughly 10 to the minus 3 full levels. And you can see that the generalization error, this is a relative L2 error. We didn't take any squares, anything. It's a standard relative L2 error, squared of some. Then you see that the generalization error is roughly like 3/4 orders of the magnitude better in this case. And the last example is the multi-input nonlinear conductivity case, so that this is for the problem, so that we plug every information, so F, G, kappa, all at once, and wanted to predict the pressure field. And in this case, here are some configurations. And similar story goes on, so that this is the trunk network training loss. We do better, like a couple of orders better, and this is the branch network training. And this is the generalization error in a histogram manner, because we have 3 inputs. It's so easy to visualize, so that we decide to do histogram. So that this is the number of the frequencies, so that we are testing on 10,000 cases, and x-axis shows the log 10 relative L2 error. And roughly speaking, we are reaching at like 10 to the minus 5 error towards, but the standard one is roughly 4 order. So we are roughly 1 order of the magnitude better in that case. So up to here is the methodology part of training method. Are there any questions before I move on to the generalization error analysis?
I have a question, Shin. I have a question.
Yeah, sure.
I have a question on the, so we know that the DeepONet is more sensitive to changing the trunk net. That's why when we do transfer learning, we are very careful with the trunk net, and we just actually change just the trunk net. But what I think you have introduced here is, so you take T to BR minus 1, the QR process. So basically you're left with Q. So you have an orthonormal basis.
Right.
Can I do that with Gram-Schmidt? I mean, the same thing. I can take the basis of trunk net, and from time to time I can do a Gram-Schmidt on the trunk.
Yes, you can do that, because the basically QR factorization is equivalent to applying the Gram-Schmidt operation based on the output sensor point, so that if you have some well-structured, I mean, even in practical case, whenever you apply the QR factorization, you may find some of the redundancy you might have in your architecture in terms of the trunk network. Because by applying the QR factorization, you may see the rank, you may check the rank. Then based on that, you may judge that which might be more important in the sense of the representing output functions.
And the overall cost is the same or less or more?
It's quite similar, so that you can okay. So the purpose of the presentation, I only show the same number of iterations, but if you run more, actually it doesn't really change much. So that, and also the trunk network, branch network training is just a simple function fitting task, so that it's quite cheap. So the overall cost, I wouldn't say it's a big difference. Roughly, I would say the same thing, because number of the parameters being trained is roughly the same.
Okay. All right. Thank you.
Thank you. And actually, with that method, actually, this motivation actually comes from the generalization analysis we presented, so that every analysis is also highly depending on what assumptions we are going to make, so that our analysis depending on the following 4 key assumptions. So first assumption is all right, let me a little bit go over one by one. So first assumption is the operator of our interest is smooth and has a spectral representation. Then spectral representation actually one of the key components that is related to the QR factorization. And the second one is the input function space, so that we need to establish some graph norm time relation. And also we argue that the input function space is metric space. So, I mean, we will see. And the third and fourth assumption is about the trunk network and the number of sensors, output function sensors. And that is also related to the spectral representation and the branch network and the uniform richness constants. That is somehow standard way of doing it. So let me a little bit go over the details. So the first assumption is saying that the following. So the one important part is we have to have one measurement here. So that this probability measure is defined on output function space. So that here we assume that Y is weighted L2 space over this domain omega Y, and we have some orthogonal basis. Then we are arguing that, assuming that this operator of interest can be written in the following form, which is the spectral form with respect to this measure. And the second assumption is the boundedness. So for any F and Y, output should be bounded. And third one is actually quite important. So given this spectral representation, we can consider its best n term approximation, so that we just truncate up to n. And then the difference between, so this is the best n term approximation error and decays with this rate. So that is over the entire space. So this is the fairly, I would say, reasonable assumption. But the key part is the rate of convergence depending on which basis we are taking. Okay. So that is the number one assumption. And the number two is that we assume that our input function is metric space. And in that sense, and also graph norm type should hold. So what I mean is as follows. So both phases represent some discretization of function. Then the difference between two discretized values has to be upper bounded by the metric between f and g and a certain rate, which is depending on the size of the discretization point. But this is typically true in many cases. But what's make things difficult might be to analyze is this B part. So B part is basically extension of finite dimensional space filling argument to the function space. So what this argues is that, all right, for any k, there exist k input functions such that your distance between any f versus among k has to be well controlled. Without this property, we cannot guarantee any generalization over certain function space. So B actually plays a key role identify on which DeepONet can be generalizable in that sense. And actually there are multiple examples that satisfy these two. So one is the, let's say we have a constant function within just one unit circle, and one otherwise, then with this metric, then actually the two properties are satisfied. And another one is the continuous function with the bounded C1 norm. And bounded C1 norm in the bounded domain is an ellipsis function, so that actually everything can be well controlled. And in that case, our metric is the L2 norm of the F minus G, then this is well satisfied. And there are more, but I skipped that for the interest of time.
Yeonjong, can I ask, in the previous assumption where you have the convergence rate depend on the basis, that's a little weird, because the basis determines sparsity in harmonic analysis, but it doesn't affect the regularity of the function of what you're trying to approximate will determine the rate, not the basis. The basis, like you have spectral basis, Chebyshev or so on, that will determine the sparsity, but not the rate in the spectral representation, for example. So that's a little weird if the rate depends on the basis.
Okay, now I see where this might come from. So, okay, I think the way I rephrase might giving you confusing, but what I'm trying to say here is, okay, I didn't specify any orderings here, right?
But you have a complete basis. If you have a complete basis, it really shouldn't matter on the rate. The sparsity, what the basis does is sparsity and conditioning, but not necessarily the rate, right?
Okay, you may have a different basis, right?
Yeah, but the rate depends on the regularity of what you're trying to approximate, not the basis itself. The basis, think of the spectral expansions.
Right.
If I change the basis, I don't change the rate. I change the sparsity of the problem.
Right. So the sparsity corresponding to this n, right?
Well, yes, in principle, you will have.
Right. Okay, I think it starts with this one, measure first. So the measure determines the basis, right?
Sure.
And what I meant is that is corresponding to affected to this rate as well. So that
anyway, just continue. It's a statement that I wouldn't like to do in my classroom.
Okay. Okay, let me first move on so we can get back to that again. So, okay, that is the so second assumptions on the space. So that somehow characterizes on what function space on which the DeepONet can generalize. And third one is trunk network and the number of output sensors. So here I introduced this T, which corresponding to orthogonalization process of the trunk network. So that first of all, I determined so-called feasible network parameters for the trunk network. So what I mean is, first, I will focusing on set of trunk net parameters on which there exists the transformation orthogonalization process, such that our trunk network form an orthonormal basis in L2. Then that actually creates certain number of orthonormal bases with respect to given measure and the given space. And the feasible parameter space I'm looking at is the one that satisfies this relation. So that given the orthonormalization, now we have n spectral bases formed by trunk network and their supremum and summate L2 norm supremum. It should be finite. And on which I will going to search our trunk network. So that is the first assumption. And the second assumption is the random samples and how many samples do we need. So what I mean is, all right, so our output sensor points are assumed to be IID from the measure that I mentioned earlier. And how many of them are needed has to satisfy this relation. So that this is the one that I show you here, and this supremum over entire function f we are under the consideration. So this is the two key assumptions, but actually this is motivated from this nice work from Albert Cohen and Davenport and Leviathan back in 2013, on which they show that the least square analysis on a stability analysis on the least squares. So they considered a similar problem, so that but the neural network case is slightly different because our basis is subjected to change. So what they consider is the following. So they're given finite dimensional subspace of L2, so given the measure, and looking for the projection error. And then, since this projection approximated by least square, so this is the least square problem. And in terms of the stability, one of the core part in their analysis is trying to get the orthogonal metrics in terms of expectation of the random samples. And this is the key quantity that appears. So this quantity is corresponding to this notion. So L2 norm squared, so that is corresponding to square summation of all of the orthonormalized trunk network and then supremum over point Y. So that is corresponding to this quantity. And what's important is that this value should be independent of choice of the orthonormal basis. So that is the one of the thing that this paper is talking about. So independent of orthonormal basis, then actually every story holds to satisfy this. In recent term, it's also generalization error analysis. So expectation is taken over random samples. So actually, we try to generalize this argument over neural network space, but neural network is subject to...
Yeonjong, can you go back to it? Because in that estimate, the second term has a growing, it's growing, right? In the Cohen paper. If you go next,
here.
Yeah. So L is what? The domain, what is it?
L is the maximum value that F can have, original target function can have.
Oh, I see. So it's finite, right? It doesn't change.
Yeah, it's finite. So n goes to infinity. So here n is the number of the samples, which corresponding to the number of the output function sensors. So that when n goes to infinity, actually goes to 0. So this term goes to 0.
And m is
number
what?
of the bases. Number of the bases.
Okay. All right. Thanks.
Yes. So actually, this provides us to a way to control the generalization error over trunk network. So that is the one of the core idea we rely on it, and on which we generalize these conditions over neural network space. So that's why we have this kind of condition. Okay.
Can you explain this? Can you go back? Can you explain this? Because it's less than my, and my increases.
Okay,
My
here.
over log m. No, not on the theorem. On your stuff. The previous, this one. So the supremum over the parameters in the trunk is less than the number. My, you said, is the number of bases, right? That you have before.
My is the number of the random samples on the output function sensors.
So as you increase the number of samples, this becomes bigger.
Infinity. Yeah. My goes to infinity, then the upper bound goes to blow up.
Yeah. How do you use this assumption here? Or B? How do you use B in assumption 3? Where would you use that?
Okay, so this actually guarantees the uniform stability of this gram type matrix, so that some ensure us to have this type of analysis over a class of the trunk network parameters.
Oh, I see. The epsilon is the same term, similar.
Yeah, epsilon being stays same, and what being affected is this the projection error, and the later term it remains to be the same because L is the property of F, not our approximation. So that what is being affected is this part.
Okay. Okay. Thank you.
Okay, thanks for great questions. All right, the last assumption is more or less the standard thing that's being frequently used in other generalization error analysis. There are a couple of ways you can address, but I followed the way I developed, which is the uniform boundedness of the Lipschitz constant, which I used in this first pin analysis paper. So assumptions are pretty standard, but I just focusing on the two-layer Lipschitz activation function, and assuming the width is sufficiently large enough so that we achieve the zero training loss, and the uniform boundedness kicks in to control the generalization error on branch part. So combining all together, we can have nice generalization error analysis, so that this is the definition of what I mean by the generalization error. So that this is our G is our operator of interest, and F is any function belongs to our target input function space. And this is our operator measured in L2 norm, the continuous L2 norm. And also the same measure being used here. Now, what we have shown is as follows, so that this expectation should be understood with respect to the number of the random output sensor point that I pointed out earlier. Then we have 4 error terms. So N is the term, the width of the DeepONet, and the rate. So that's why it is related to the mu star, because the trunk network, we are looking at the parameters on which somehow figuring out what would be the best N basis that represents the given data. So that is corresponding to kicks in this part. And the K is the number of the data we use, so that, and MX is the number of input sensor point. And these two are related to how we define our input function space and ask whether it satisfies the graph-norm relation. So two are involved. And the branch network actually plays a key role to determine the constant of this in front, this two term in front. And the last one is the output sensor. So that you may see that this my minus r is similar to the Cohen's one here. So that is where it comes from. And in terms of a little bit of the rate, so that R is any number between 0 to 1. It also affects to how many my being determined, but that once, as long as R is being fixed, then it's okay number. And alpha and S, so alpha and S, this is the crucial in a sense that it is highly related to which function space we wanna train over and also wanna generalize over. So that characterization of X is actually plays a role to determining these two. And then the trunk network basically determines what kind of the orthonormal basis they are looking for. And then it actually results in this determines this rate. And the branch network, affects to the constant part of this. So this is our main result for the generalization error analysis. So in a nutshell, for control the generalization error over branch network, we follow the standard approach, what I have done before. For the trunk network, we actually extend the Cohen's work to over parameter that somehow mimics the uniform law of large number in that theme over uniform law, not that exactly uniform law, but uniform over that number of the criteria being required for the sampling.
Yeonjong, can you explain for the input for the branch why K and MX? MX is the number of sensors, which is a training data also, right? Or not?
MX is the discretization of F input.
Right.
Yes.
So that so like, for example, that would be like the projection error, if you right, the encoding, let's say, error from the input.
Yes.
It's a uniform, it will be 1 over MX, for example.
You're right.
Yeah. Now, K, what is K?
K is the number of the data point in the pair. So let me a little bit go back.
Isn't that defined by the number of sensors?
No, this okay. Let me a little bit go back to.
Sorry, no, you're right. No, you're right. You're right.
Okay. So that's the total number of the data pair, input output pairs. So here.
Yeah. Okay. I'm just trying to think if it's different, because if I have 100 sensors for an F, I will have 100 pairs, right?
Right. I think you asked quite a right point. So that here I am mentioning space filling argument on B, and B is the only place where K appears.
Okay.
So that MX is the discretization point. So that okay. So roughly speaking, if the MX is sufficiently large, it should be approximately recover the distance between F and G in function level.
Right.
So that is about A. So A is only concerned with how many MX do you have for the discretization sense.
Right.
And B is concerned with how many functions do we need to cover entire functions space.
Okay.
So that's where the K comes into the play.
And S is what? S
okay,
is
S it's depending on what is your X. So
H1
okay.
or H something.
So for example, in this example 1, which is the constant function case, I think this is the S equal to 1. Okay. And example 2 case, actually, it is depending on MX, actually.
Right. So okay, that makes sense, because I thought the two are related, so that I see two independent components in the error, so that confuses me.
Right. That's a fair point. So yeah, that's quite sensitive. So I think that's where the main thing that determines in a certain learning task, actually, with a small number of the data points seems generalized as well. And if that is the case, the function input function space being under the consideration has some nice property on S. And if the certain cases seems like if the generalization being struggling, and that is probably related to this rate is being quite acting in a adversarial way.
Yeah, and you don't cover the function space fast enough. Yeah, I think
yes,
that makes sense for the generalization area.
You get the right point, George. Yeah, so that's somehow I was hand waving here. Space filling argument generalized to the function space. So that's what I meant this point.
Thanks.
Okay, then let me quickly wrap it up. So yeah, that's it. All I have. So we presented the two-step method. The core part is separation of trunk and branch, and the QR plays a key role that improves the generalization and stability. And we presented the generalization error analysis, which based on Cohen's old paper on the stability and accuracy of the least square analysis, and we generalized that analysis in the context of the trunk network. And that somehow covers the generalization part concerning trunk. And two-step actually plays a role because that is rely on the least square analysis, and we are assuming that branch network learns the least square solution. So there is a connection there. So, and generalization analysis is done, and this is a reference, and thank you very much.
Thank you, Professor Shin, for your great talk. To me, it was like a course lecture with all the details. So is there any question for the speaker from the audience?
Amelia had a comment in the about the partition of unity. Amelia, are you online?
Hi, Josh. Yes.
Do you want to
So,
say what you want to talk to, because he hasn't seen your comment?
It was just a comment, Yeonjong. Basically, what we have proposed is we are enforcing this partition of unity property through the basis function. So what we are doing is we are just summing all the basis function and equating it to 1. So this is similar to what you are proposing, that the T matrix where you are enforcing the orthogonality, right? I mean, that was just a comment. I'm not sure if
thanks for the comment, but I think orthogonality and the partition of unities are different thing.
But they are both required for orthogonalization, right? I mean, the partition
Partition
of
partition of unity, you require some to one.
yes, yes.
That doesn't mean they are orthogonal.
So yeah, I mean, of course, we are not enforcing the dot product of these basis function to be 0. But still, I think it has some consequences on the orthogonality properties of the basis function.
Okay. I was expecting maybe some relation to POD net, but I didn't thought about POU net.
Okay. But yeah, thanks for the talk.
He has a paper on the archive, but there's no analysis in that paper. We just use it. So you may look into it, Yeonjong.
Yeah, sure. I think I read it through before, but I found might be closest one is PODNet, although PODNet utilizes SVD directly.
Right. No, this is not the
I see.
not the POD. This is the partition of unity, and I think not Trask also.
Right.
It's something not for the DeepONet, but something similar.
I see. Yeah, I will double check with the POUNet. I think there's some orthogonality. I saw a couple of work trying to enforce the orthogonality, but I found that it's quite difficult to enforce orthogonality at the same time of the training. So that's why our step 1. So I think one of the key steps we have is this step, because A is supposed to be branch network, but we just replace it to just a matrix A. So what this is basically asking is find the best parameter for A. So that A represents to what branch network supposed to learn in a certain sense. Then phi, because we're targeting at the U here, which is our function information, so that at this step asking basically find the right representation, the trunk network. And then A is being obtained. Then A is the something that branch net should follow. But along the way, we found that because the neural network somehow not orthogonalized, so that branch network has some redundant information associated with the trunk network. And we found that by orthogonalization, somehow those can be done very efficiently. Yeah, that's, I think, what.
Yeonjong, have you tried to visualize the basis?
Yes, we did, but it's quite a nice figure, but I wasn't sure what to say about, so I didn't put it in a paper. So it's a nice figure. So like first mode seems to capture the majority of the shape, and the second mode, so in terms of like the eigenvalue, the values of the eigenvalues, not exactly eigenvalues, but corresponding to the, you know what I mean. And the second mode trying to captures the errors, etc. So they somehow shows the similar behavior of the TOD type shape. So it was quite a nice figure, so that I can clearly see that the importance of QR factorization, because if we just plot the neural network, for example, ReLU, it just to show, just to like piecewise linear shape, but after the orthogonalization, actually it actually captures the common features inside of the
Do they look like spectral modes, more zeros of cluster at the boundaries, for example?
It highly depending on the problem. For example, the discontinuous shape. So it's okay. So it's totally different shape. So wasn't quite sure what kind of basis they are finding per se, but somehow this is some empirical orthonormalization, not respect to the quadrature point. So if there is some quadrature point with the weighted and apply the QR factorization, I think that might be more valid characterization of what you meant by the spectral basis corresponding to. So this is somehow empirical orthonormalization process given our sensor points. But in the applications, the sensor points are often not freely chosen because we have to solve through the numerical solver. So that there's a little discrepancy. I suspect that might be one of the reasons that might be one of the case. And also in terms of the orthonormal basis, because when we use the polynomial basis, we know that the certain degree, although we somehow apply transformation, we know certain degree so that there's some well-controlled way that we can see how things are changing. But my perspective is that somehow they are trying to mimic similar procedure, but somehow find a more data-driven spectral basis, I would say, in that way.
Because Andrew Stewart, in one of his papers, had tried to visualize it, I think, in 1D, and he was getting some inconsistent results, especially for discontinuous problems. So that's why, so it's actually interesting for the two problems that you have. If you have any visualizations of the basis for the two problems, the continuous and the discontinuous second part, I would like to see them.
Okay, I will send you a separate email because I already saved them all before, but decide not to plot it because they already more than 20 some pages. So yeah, I'm happy to send it to you. Actually, quite fun to see. It's quite for smooth problem, it's quite a spectral behavior, but the discontinuous one seems like, yeah, it's quite an interesting figure. But yeah, I will send it to you through email.
So what Stewart found is that for the discontinuous problem, he was getting a more global modes, which didn't make sense because I would expect if they're data-driven modes for discontinuous to have more localized modes. And so that was kind of why I got confused. I don't know what's the answer, but
okay, I see similar thing because for the discontinuous case, the first mode actually captures the overall shape of the discontinuity, like in the center, and discontinuity happened in the circle. And the second mode actually trying to capture the noise around the boundary.
Okay.
And third one is keep capturing those so that I see similar behavior. I think the reason for that is because of the ideally, one basis is suffice in a certain sense because of the neural network capability. Then for this type of the discontinuous problem, all we need is just to find this shape and multiply by a certain number because we are only changing this shape.
Yeah.
So that ideally that is supposed to be the one, I believe. So that I think that is well shown. But let me send you some of the images that I have with you.
If you plot the standard the vanilla DeepONets, they're oblique, right? So they're contributions from one mode to the other. So but now in your case they're orthogonal, so it actually makes sense to examine the modes and the hierarchy of the modes.
Right. I see.
So, but anyway, that's a great contribution. Congrats.
Thank you very much. But I will double check with the rate. But yeah, thanks for the comment. And also great to see you.
Yeah. Is there any other question?
Hi.
No.
My name is Vivek. I'm a PhD student working with George. Hi, Dr. Shin.
Hi,
So I
Vivek.
have a quick question. So I just want to know your opinion on why QR will work. I think the same framework can be used even with an SVD perspective. Like you can train unlike the POD DeepONet in which you directly feed the POD modes instead of the trunk network, you can train the trunk network softly to approximate the POD modes, POD basis. So as against that, why will QR be better? Is it because it is faster or any other reasons? Can you please say a few comments on that?
That's a great question, but I don't think I have a good answer because it is depending on what problems are you looking at. If the standard POD okay, if we are working on the problems on which the standard POD way works well, then I think the way, okay, if that is the case, the contribution of the DeepONet is to learn the branch network, right?
Yep.
Then branch network should targeting the rest of the SV, the POD on the data and capture the entire thing. So if the standard POD works well, and then POD approach also works well, but okay, it is my impression that what's more important seems to me that the branch network, because the trunk network somehow can be learned quite well, even just to feed forward the neural network. But I think the Lulu mentioned one time, but the branch network architecture has some inductive bias some way, intertwined way, so that capturing that actually quite hustle. So I think the reason, one of the reasons why PODNet worked quite well compared to the thing might have some similar consequences.
Okay.
So that they somehow separated the training, the trunk and branch, and then trunk being done, then focusing on the branch and whether see if they can capture branch well. And if the branch is well designed so that happen to generalize as well, then that's a good model compared to just standard POD, because you have to solve the coefficient every time. So I think that's the where the benefit. I think that I think the general idea stays hold, so that of course it depending on the application, because also after this one, some of the colleagues wanted to try their problem on this, and that actually data changes the geometry over the data. If that is the case, then actually capturing trunk is become a hard job.
Right. Yep.
Obviously, if that is the case, then POD wouldn't really work well, but separation actually helps understanding which task you want to focus more.
Okay.
And once the trunk being successfully trained, now you can focus on the branch.
Yep.
And that somehow save lots of the GPU memory and the time and focus. So that's how I view it. Yeah.
Okay. Thank you. Great talk, Dr. Shin.
Thank you.
Raj, do you want to ask a question?
Yes. Hello, Dr. Shin. This is Raj. So
Raj.
just extending the Vivek's question, wouldn't depend on the type of the matrix, whether it is well conditioned or the badly conditioned. So then stability of the QR will depend on the conditioning of the matrix. So wouldn't that depend that whether we use QR or QR decomposition or singular value decomposition?
That's excellent question. So
because if matrix is rank deficient, then QR will do the decomposition, but that will not be reliable. But SVD will give although it will be slow, but it will be reliable. So that's why it depends on the nature of the matrix actually.
That's a good point. I think that part can be addressed by the choice of the width, actually. Okay. So in this part, so that the size is actually, the column size is n. Then if the U has a rank deficient, that's fine. But as long as the rank is greater or equal to the choice of our neural network width, n, the DeepONet width, then that problem can be handled in this particular scenario. But you're right in the sense that if you just work on by applying SVD on U, then you have to somehow truncate some mode, and that somehow determines the width of the network, exactly. Right?
Yes.
So I think there is some. So I think the width plays a role in that case.
Yes. Okay.
But if the width is too large, then I'm with you. I probably encountered that issue.
Yeah, because I for well conditioned and non-rank deficient matrices, QR is very good, like better than SVD. But yeah, so that's
Yeah.
that's
Okay.
I think a good intuition that width will determine the conditioning of
Yeah.
the matrix.
Actually,
Yeah.
that's a very good point. As you may see that our width is 50 here, as you may see, so that
Exactly.
we
Thank-
somehow control that part. One hand, actually, I didn't realize that the part, but I tried the one thing that is super large, but isn't not really applicable because of the rank thing. You're
Yeah.
right.
Yeah, yes. Also, just a question, two questions. The first one, the QR will be the part of the loss. So you have to differentiate through the QR. Am I right? Like
Okay,
when you
okay, to QR apply in the separate procedure. So,
Okay.
Okay.
So that is why your
Uh,
complexity doesn't change much, computational complexity.
Exactly. QR is not part of in an iterative procedure. So once it is done, then we apply QR just once to
Okay.
fix the T transpose. So that's why I was trying to say that the overall cost doesn't really change much in that way. So that
Yeah. Yes. Also, did you try it for any time-dependent system?
that's a great question. I'd love to try. I haven't tried yet.
Because in that case, input space for trunk net will change because time will come in. So
Exactly.
So I don't know how the analysis will hold for that kind of system. So yes.
That's a good comment. I feel that would go along with the traditional reduced order modeling type analysis that
Yes.
the chomorograph and width comes into the play.
Yes.
But we need some more generalized notion that incorporate the trunk network type basis, so
Yes.
that I think applying the QR, so that I think the main thing is if we transform our trunk net turns into some type of orthogonal basis,
Yeah.
then that somehow connect through some existing linear analysis. And on top of that, some uniformity comes into the play, like similar inspiration of like uniform law of large number type, then I think that can be addressed in a similar way.
Yeah. Yeah.
But that's good. That's a good comment. I haven't thought of, okay, so to be honest, I haven't thought about it too much, that part.
Yeah. Yeah. Because in our experience, it's a very tricky to train DeepONet for time-dependent system. Like if you have a system like Kani layered or LN-Kan type. So
Right.
So I think notion of basis it changes actually in that way. So I'm not very sure about the analysis part, but yeah, very great talk, very nice informed. So thanks.
Thank you very much.
So is there more question? No. Thank you for your great talk. Thank you everybody for your participation. And I want to close the session. So have a great rest of the day and have a great weekend.
Thank you very much.